In this example, we're really doing a similar thing to worked example 5, which is using the idea that dy dx, which is what we want to find, the derivative of y, is equal to 1 over dx dy. So it's basically finding dx dy and then flipping that over. Okay. This particular question is asking you to find the gradient of a curve. Now, as soon as you see that word gradient is dy dx. It's the gradient function, which is the derivative. So you're asked to find the gradient of the curve given at the point where y equals 3. So that means not only do you find the gradient, but you then find the gradient at a particular point. So we can do that. So first thing we have x, oops, put the pen on, x equals y squared minus 4y. What we're going to do then is we're going to differentiate both sides with respect to y. Okay. So I'm just going to write the equation out again. You can see I've left a bit of room because I'm now going to put my differential operator in. I'm just doing this in a different colour so you can see it. Differentiating with respect to y. Why? Because the function is in terms of y. So that makes sense. It also gives us the dx dy that we needed here. So on this side we now have dx dy equals. This tells us we must differentiate what's in here. Variables match, so you just do it the same as you would normally if these were x's. So this would become 2y. Oops, I'll just do that again. Okay, now what we have, or what we need, is we need dy dx. So we're going to flip both sides. So flipping the left side, we get the dy dx that we need, equals, remember that if you can't obviously see a denominator, the denominator is 1. It's all over 1. So I'm just going to flip this over now. So we have 1 over 2y take away 4. Okay, that's the gradient function. So I'm just going to label that as such. This is the gradient function. Oops. And often we write the gradient function using the different notation, which is y dash x. And that's particularly useful when you have to substitute particular values of x in there as well. So you can use either way. Today, because we're looking at points where y is a particular value, I'm just going to leave it in this form. So the gradient when y equals 3 is going to be dy dx. The gradient would be 1 over 2 times, and y is 3. This is simply a function of y. So we've got 1 over 6 minus 4, which is 2. So what that means then is that at y equals 3, the gradient of the function is equal to a half. So that means we have a gradient of a half at the curve at that point. And what you might like to do as well, which you could do, is to put the 2, or the 3 I should say, the point y equals 3 into this function. And you can see that x equals, when y equals 3, x equals 3 squared minus 4 times 3, 9 minus 12, which would be minus 3. So you'd actually have a point, oops, which is minus 3, 3, with a gradient at that particular point. The gradient would be a half. So if you were to look at this function and look at what the gradient would look like, it would be a half. So it would be a positive gradient and not particularly steep. But in terms of what the answer that's required for this question, you don't need to go to this point finding a coordinate. All it asks you to do is find the gradient of the curve at the point y equals 3, and that is simply a half. Use your CAS for worked example 6, you could do that. So what you're looking for is dy dx, and what you could do is actually put in, you know that on the left side you're going to get dx dy, so you can actually differentiate the function using calculus and then derivative, d dy, so differentiate the function on the right, which was 2y take away 4, okay, which you find very quickly is 2, and then you know that dy dx is the invert or the reciprocal of that, which would be a half. So you can use your CAS for these questions.